Hello, this is Team Takeo Comfort Solutions for the SmartPlug Bluetooth button and transmitter and receiver. Our technical directors are Philip Manning, Nick Costello, and Rob Kalicker. And our team members are Andrew Nebraska, Daniel Sosa, Matthew Moreno, and Michael Correa. Here's just a picture of our technical directors. Rob Kalicker is on the left. He's the VP of Research and New Product Development for Takeo. Philip Manning is embedded controls engineer for Takeo, and Nick Costello is software engineer for Takeo, and Mike Smith is the consulting technical director. Here's our team composition. The first one off to the left is Andrew Nebraska, electrical engineering. Second picture is Matthew Moreno, also electrical engineering. Third picture is Michael Correa, electrical and computer engineering. And the fourth picture is Daniel Sosa, computer engineering. Company overview, family-owned manufacturer of heating, cooling, plumbing, and irrigation products, affordable products that save energy, and headquarters are in Cranston, Rhode Island, and facilities also in Vietnam, Switzerland, and Italy. The motivation for the project is a SmartPlug Bluetooth button transmitter receiver. It's for low power Bluetooth communication, save energy without wasting water, and smart learning with a phone application. And off to the left is a picture of the systems. The motivation again for the project is for homeowners, business owners, and water authorities. The importance of the project is the Bluetooth communication and the fault backup. Places of interest for this project include places where there are significant droughts that occur more often. And the only thing that really needs to be worried about with this project are regulations and roadblocks, which the pump must manually be turned on, and no device learning for start, and it must follow individual state guidelines for hot water heating. The anticipated best outcome was to develop the hardware and firmware for both Bluetooth button and SmartPlug module. For the key features of SmartPlug was Bluetooth communication, control SmartPlug functionality via GPIO and drivers, update SmartPlug firmware to provide on-demand recirculation functions, prototype button board, the coin cell battery operation for 5 to 10 years, push button, and Bluetooth communication. The anticipated best outcome was not achieved. Even though we spent countless hours, countless days on this project, we unfortunately were not able to reach the anticipated best outcome. That was due to a couple roadblocks as far as scheduling and delays in getting key things that we needed in order to get the project done, which includes project files and getting stuff downloaded. What was achieved was we created a cutout in the casing of the SmartPlug prototype for safe testing, and we also revised the schematics and layout for the SmartPlug to allow for hopeful final prototype of the SmartPlug, which will ultimately be used for the final product. The summary of the team key technical accomplishments includes revisions made to the schematics for the SmartPlug, implementation of the permanent Bluetooth module used for final product along with proper circuitry revised in accordance with the final product, revisions made to the SmartPlug layout in accordance with the schematics to allow for it to be made and fabricated in the future, safe onboard testing for the SmartPlug circuitry, uploaded Flutter demo onto Android phone, Flutter Blue Plus instead of Flutter Blue sample for Bluetooth low energy, and find other devices to connect to for the mobile application, which allows for less bugs. The economic impact for the company with the development of this device, it would realize increases on demand and the product sale in the range of $380K to $475K annually, but could be more depending on if the demand is more than what it is projected to be. Here is a block diagram of the product. So off to the left is more of a hardware side of it, which includes the button and then the SmartPlug, and then which is connected to the pump. On the right-hand side is the software, and that takes steps through all of the elements that make up the software and how the product works. So for technical accomplishments for schematics and calculations, we made necessary corrections to SmartPlug schematics and performed calculations for SmartPlug schematics. For the SmartPlug corrections, we made revisions to the schematics on pad software based on revisions that we had made by hand previously at the beginning of the year. based on feedback received by technical directors. We added components, which include the permanent Bluetooth module, the micro USB port, voltage regulator, crystal, decoupling capacitors, and 3.3 volt rail. And we also made calculations for the SmartPlug circuitry, perform the calculations to verify components validity, and calculations made by hand, mostly voltage drops, which is what was calculated. And as you can see, a picture on the left is the picture of the original schematics, and then the picture on the right is the revised schematics based on all the changes that were proposed. For the layout corrections, we moved, deleted, and added new components to the SmartPlug layout. Move components, had to move a number of components in order to add in newly added parts. Can only make revisions to low voltage components since no new components can be added to the high voltage side and have to stay on the low voltage side. And adding and deleting components based on which components we added in, which were new components or components that were outdated and that were in the old design that needed to be changed based on the new design for the final layout. And as you can see, this is a picture of the layout on the right. This is the one that I was working with. And as you can see, kind of cut right across the middle is the line of the high voltage side and the low voltage side. The high voltage side is all the blue or the light blue colors, and the low voltage side is all the yellow. For onboard testing the validity of circuitry for the SmartPlug and prototype itself, we perform safe onboard testing. In order to allow safe onboard testing, we need to make a cutout in the design casing to access temporary Bluetooth module. The onboard testing of the LED error, mode, LED power, external sensor, and mode button circuitries. And we tested to check the validity of the circuitry and correctness of the circuitry based on the previous offboard testing. As you can see off to the right is a picture of the cutout of the casing to get to that temporary module so we can test it safely. And off to the left is just the onboard testing for just the LED error, LED mode, and LED power actually working. And for the prototype button board, I assisted my fellow electrical engineer, Matthew Moreno, in testing and soldering the prototype button board because there were so many roadblocks and issues with the prototype button board. It did require a lot of work and time and effort. So we desoldered and soldered components onto the board and onboard testing for the prototype button board to see what was going wrong and what needed to be changed, what needed to be fixed, what needed to be done. And I will pass it off to Matthew Moreno.
Hello, my name is Matthew Moreno. I'm one of the 2 electrical engineers who had worked on the SPBBTR project for TACO Comfort Solutions, and I'd like to go over some of my technical accomplishments for this semester. The first one is troubleshooting the button board. I began by testing all the inputs on the prototype button board, and I confirmed that the key components that should be receiving power were not receiving power. After confirming this with TACO, I was tasked to rebuild a new button board. The first attempt was to move components from the already existing board onto a clean one, and the second attempt was by replacing the MD-BT50 module, the Bluetooth module, with one from an Adafruit Feather, and unfortunately neither of these attempts were successful. The second accomplishment I'd like to go over is the prototype button board itself. Unfortunately, trying to hand solder the MD-BT50 requires equipment that URI does not have. So we had settled on having TACO do it back at the company. After the MD-BT50 was soldered on by TACO, I was then tasked with repopulating the prototype button board. I had to order some new parts from DigiKey, and this was a great opportunity to really put my skills to the test, as most of the board itself is surface mount, which I'm not really, which is all new to me, if I'm being honest. Lastly, I'd like to speak about the continued troubleshooting of the prototype button board. After I finished the new board, it was not able to connect to the computer. I'd let my TD at Takeo know this, and I had a meeting with Philip Manning from Takeo Comfort. In that meeting, we confirmed that the board was indeed receiving power, but not able to connect to a computer. We believe that one of the 5 pins highlighted in the picture on the right is what's causing the chip to not connect to the computer. Had we been able to x-ray the chip itself, we would be able to confirm which of the pins is causing the problem. I'd like to thank Takeo Comfort for allowing me an opportunity to work on their project, and now I'd like to pass it on to one of the CPE students in our group, Michael Correa.
Hello, I'm Michael Correa, and I worked on the computer engineering side of this project for Takeo Comfort Solutions. I am here today to discuss my technical accomplishments. First, we have the timeout error counter. It records instances in which the button takes too long to connect to the SmartPlug. It would be inconvenient to say the least if the attempt to connect went on forever, blocking all future attempts. To avoid that, I created a function that calculates how long the attempt takes, and if it takes too long, the attempt will be terminated and the scanning for Bluetooth will stop. The radio state will then become idle, allowing a future attempt to be made. Next is the 24-hour idle timer. In the event that a button press has not been initiated within the last 24 hours from a particular button, that button will then send a status report to the SmartPlug. That button will report its Bluetooth signal strength, current battery level, and the amount of timeout errors. This is so that the SmartPlug is aware that the button just hasn't been used, as opposed to the button having malfunctioned. Next is the button press time limit. This function, and the calculations within, eliminates redundancy. If the SmartPlug has been initiated and the recirculation of water has already occurred, then, for a time, there is no need to recirculate the water again because it has already been heated. In the event that a button press occurs within 15 minutes of a previous successfully transmitted button press, the most recent button press will be ignored. Last, but certainly not least in regard to challenges and difficulty, is low power mode. I regret that I was not able to make substantial progress on this feature, though I was able to conduct a lot of research and narrow down the scope. The resources on power management are few and far in between, scattered amongst forum posts that date back half a decade. After extensive research, I was able to choose the functions that most likely fit the needs of this project. I hope that I leave behind enough information to allow the next team to hit the ground running. And now I pass on the presentation to one of my co-designers, Danny Sosa.
Similarly, I also worked on the firmware side. This time around, I was focusing on a mobile application. So the first thing I had to do was figure out what cross-platform I was going to choose. I chose Flutter because there's a lot of great documentation and resources that explain how to use Flutter. I also saw a lot of YouTube tutorials explaining and showing you how to edit the code so you could get different styles of widgets and the best nice looking mobile application. So I went ahead and downloaded all the packages, and I tested different examples of programs from GitHub to make sure everything ran smoothly, and Visual Studio's code. I wanted to make sure I had all the packages for Flutter so it could run smoothly on the Android emulator. I then had a physical Android device, which makes the running process a lot faster instead of doing it on the Android emulator. So to begin, I wanted to test out the beginner program called Flutter Demo on the physical Android device, so I know it works, which it did, and it had a button for the users to press, and I showed how many times the user pressed it. I was able to edit the code for this demo application, and I was able to make the button different style, edit the home page, change the incrementation, and I was able to also change the layout and the colors and all of that good stuff. I also had to download a Bluetooth Low Energy from GitHub. At first, I went with the Flutter Blue sample. However, the owner is now currently maintaining it, and there is a few bugs that is known. So, with the help of technical director Nick, we were able to find the Flutter Blue Plus, which works a lot better. And the creator is currently maintaining it by Bosco Geach. So I was able to scan nearby devices that the Android device could connect to, just using the search icon shown in the image. I downloaded all the necessary packages for the Bluetooth Low Energy to work on the Visual Studios, and the connection to another device was successful. I just want to thank Robert Killicker, the VP Research and New Product Development, Philip Manning, the Embedded Controls Engineer, and Nick Castillo, Software Engineer, for your time. And I also want to thank Dr. Sunak, the ELECOMP Capstone Program Director, Brendan Smearback, the Senior Software Engineer who graduated from URI 2017, and Mike Smith, the Consulting Technical Director. Thank you for your guidance and thank you for your time. We all really appreciate everything you have done for us and the guidance and just being there for us when we needed you, when we emailed you, and for just giving us this opportunity. Thank you so much.